Hi everyone, it's Michael. So I have a breathtaking problem for you all today. This one was sent to me by a viewer of my channel from Vietnam, and it looks like a really simple problem, but I had a lot of difficulty with it. So I'd be really interested in if any of you have a different solution. And so if you'd like to try to solve it, feel free to pause the video. Alright, so we have a triangle ABC. I is the incenter, H is the orthocenter, and D, E, and F are the points of tangency of the incircle with B, C, C, A, and AB. And we let G be the foot of the perpendicular from D to EF. And we want to show that angle BGF is equal to angle CGI. So I already wrote out the first step of my proof, and that's because I actually ran out of the number of steps that I could show with GeoGebra. So you get a sneak peek of the very first step of my proof, but that's all you get. So I based my proof off of the Sharkydevil configuration. So if you saw on my channel the first video of the problem I couldn't solve, if you go a couple minutes into that video, you'll see we look at the Sharkydevil configuration, which is shown to me by another viewer of my channel, and I'm also going to put a link to it in the description of my video. So before I even really get into trying to prove the final claim, I'm going to show a couple of things related to the Sharkydevil configuration. All right. So the first step, it's obvious since AI is an angle bisector, it has to pass through the midpoint of arc BC. All right. And now AFIE is pretty obvious to see that it's cyclic because angle AFI is 90 degrees and so is angle AEI. So I'm going to write that out. Okay, so AFIE is cyclic, so I'm going to draw the circumcircle. And AI is the diameter since those are right angles. And I'm going to let the circumcircle of AFIE intersect the circumcircle of ABC at a point N. And now what I'm going to do, this is still part of the Sharkydevil configuration. I'm going to let AN meet BC at another point, which I'm going to call O. All right. And also, by the in-center, x-center lemma, which I've covered on my channel a couple of times, M is the circumcenter of triangle BIC. So I'm going to write that out. So M is the circumcenter of triangle BIC. So there's a circumcircle. All right. So MI is a radius of that circle, and AI is the diameter of this other circle. And so from there, it's easy to see that the two circles have to be tangent at point I. All right. And once we know that, then it follows that OI has to be tangent to both of these two circles by the radical axis theorem. So if we take these two circles and the circumcircle of triangle ABC, the pairwise radical axes are AN, BC, and the tangent at I, and so that has to pass through O. And so in other words, OI is tangent to those two circles. All right. And once we know that OI is tangent to those two circles, since AI is the diameter, that means that angle OIA has to be 90 degrees. So we have angle OIA is 90 degrees, and angle OJA is 90 degrees, and so OJIA is a cyclic quadrilateral. So I'm going to draw that in. This is all still the Sharkydevil configuration. All right. So where do we go from here? My goal is to show that N, D, and M are collinear, and also that N, G, and I are collinear. So I'm going to try to prove those two facts. First, I'm going to start with N, D, and M. Now, in fact, I'm going to show that not only are those 3 points collinear, but they're also collinear with this intersection point right here. So if I take the intersection of the circle AFIE with the altitude AJ, so I'm going to label that P, I'm actually going to show N, P, D, and M are all collinear. So the first thing to notice is that it's not hard to show that IPJD has to be a rectangle. So I'm going to write this out. I just drew an IP and ID. An angle IPJ is obviously a right angle, since angle IPA is a right angle. An angle IDJ is also a right angle. Okay, so IPJ, it's 180 minus IPA, and that's a right angle since AI is the diameter. So IPJ is 90 degrees, IDJ is 90 degrees, and also obviously PJD is 90 degrees. So IPJD is a rectangle, so I'm going to use that. All right, so first I'm going to show that NP and D are collinear, and I'm going to do that by an angle chase. Okay, so we have angle IPD is equal to angle IJD. That's where we use that's a rectangle. And IJD is equal to angle OAI. That's because OAIJ is a cyclic quadrilateral. And so angle IJD, that's the exterior of angle OJI. And so it has to equal the opposite angle in that cyclic quadrilateral, which is angle OAI. Angle OAI is equal to angle NAI, and that's equal to 180 minus angle NPI, since NAIP is cyclic. And so if angle IPD is 180 minus angle NPI, then that means NP and D are collinear. So I'm going to write that out, draw in that segment. And we can do a very similar angle chase to show that N, D, and M are collinear. So I'm going to show you how I'm going to do it here. Since M is the midpoint of arc BC, we can draw the tangent to the circumcircle of ABC. So I'm going to do that. And it has to be parallel to BC, obviously. And I'm just going to take another random point on it. I'm just going to call it Q just for reference. But now I'm going to do an angle chase that shows that ND and P are, or ND and M are collinear. All right, so here's that angle chase. So angle NMQ, that's the angle between NM and the tangent at M. And that's equal to angle NAM, which is the same as angle NAI. And that's equal to angle, this should be IPD. So angle NAI is equal to angle IPD, because that's the exterior of the opposite angle to NAI. And IPD is equal to angle PDJ. Okay, so we have angle NMQ is equal to angle PDJ, but QM and DJ are parallel. So since BC is parallel to QM, because M is the midpoint of arc BC, from this angle equality, it's easy to see that PD and M have to be collinear. Okay, so that finishes off that collinearity. All right, and so now I'm going to hide a bunch of stuff. So all this stuff that I did, this is almost the end of the Sharkydevil configuration. So I just used point O to prove that NP, D, and M are collinear. So now I'm going to hide it. But now I'm going to do a little bit more. So here's something, if you watched the video on the problem I couldn't solve, which was the second live stream on my channel, I ended up proving that triangles BFG and CEG are similar. And so I'm going to do that again right here, just sort of rehash that proof. So I let EF and BC meet at a point, and I'm going to call that R. Okay, and now I'm going to do something that I've done many times on my channel before. So it turns out B, C, D, and R have to be in harmonic conjugation. And so the proof is fairly quick. So A, D, B, E, and CF are concurrent by Cheva's theorem. That's easy to see. I've done that a couple times on my channel. And so because of that, that means that B, C, D, and R have to be in harmonic conjugation. So this configuration, I think it might be video 55 on my channel that I talk about this. So if B, C, D, and R are in harmonic conjugation, an angle DGR is 90 degrees, because that's how G is defined basically. then that means that angle BGD is equal to angle CGD. Okay. So we have angle BGD equals angle CGD. And if that's true, then it follows fairly easily that angle FGB is equal to angle EGC. That's because if you just take these two equal angles right here and you do 90 minus them, you would get angle FGB is equal to angle EGC. Okay, so that's one of the pairs of angles in the triangles FGB and EGC. And now I'm going to show that another pair of angles is equal, so that obtuse angle, which is not hard to see. So angle BFG, it's 180 minus angle AFE, which is 180 minus angle AEF. That's because triangle AEF is isosceles, and 180 minus angle AEF is angle CEG. Okay, so basically in these two triangles, FGB and EGC, we showed that two of the three pairs of angles are equal, so those triangles have to be similar triangles. So I did this exact thing in that earlier video I mentioned on the problem I couldn't solve. And so that means that we can do some ratios. So I'm going to write it out here. So that means that FG over GE is equal to BF over CE due to the similarity. And BF is equal to BD because they're both tangents, and CE is equal to CD because they're both tangents. So we have FG over GE is equal to BD over DC. All right. So where do we go from here? What I'm going to do is I'm going to note something. So if you look closely, a spiral similarity takes triangle NFE to triangle NBC. So, and that spiral similarity is centered at N. So if you've watched my video on spiral similarities, if we want to find the center of the spiral similarity taking FE to BC, well, we can connect BF to CE, they intersect at point A. And if we find the intersection of the circumcircle of AFE with ABC, which is N is the center of that spiral similarity. All right, so basically, said another way, that means that, so first of all, triangles NFE and NBC are similar. But not only that, the whole quadrilateral NFIE and NBMC have to be similar because I is the midpoint of arc FE of the circumcircle of NFE, and M is the midpoint of arc BC of the circumcircle of NBC. Okay, so these two quadrilaterals are similar, and not only that, from this ratio up here, G breaks up the segment FE into the same ratio that D breaks up the segment BC. So basically, D and G are corresponding points in those two basically similar figures. They break up the corresponding diagonals into the same ratio. And because of that, since N, D, and M are collinear, it follows that N, G, and I have to be collinear. All right, so just to state that again, so in these similar figures, G corresponds to D, and I corresponds to M, and N is essentially corresponds to itself in these two similar figures. So since we showed N, D, and M are collinear, then N, G, and I also have to be collinear. All right, so finally, I am going to try to get started on the actual problem we're trying to solve. So we want to show angle BGH is equal to angle CGI, but we know angle BGD is equal to angle CGD. So I wrote that somewhere up here. Let me see if I can find it. That's right here. So angle BGD is equal to angle CGD. So solving the problem, it's equivalent to showing that angle HGD is equal to angle I or angle IGD. So basically, if we extended GH and GI to meet BC at 2 points, then we'd want to show that we have another harmonic conjugation. So before I get too much into it, I'm going to do something here. So first I'm going to show that N, G, D, and R is cyclic. And that's true because if we look at the similar figures that I mentioned, the angle that NI makes with EF has to be the same as the angle that NM makes with BC, because those two pairs of segments in the figures correspond to each other. So basically NGF is the angle between NI and EF, and NDB is the angle between NM and BC. So if NGF is equal to NDB, that means angle NGR is equal to angle NDR, and so NGDR has to be cyclic. All right, so now I'm going to draw in a couple more segments here, like I mentioned. All right, so basically from what I said earlier, we want to show that GD bisects angle TGS, because if we could show that, then we could subtract it from this equality, BGD is equal to CGD, and that would solve the problem. So how do we show GD bisects angle TGS? So here's where it starts to get interesting. So that's the same as showing that TS, D, and R are in harmonic conjugation. And that would be the same as also showing that ND bisects angle TNS. So some of you may know about Apollonius circles, so you may recognize this. But basically, if we can show that ND bisects TNS, then that's the same as showing that GD bisects TGS. Okay, so I'm going to show that ND bisects angle TNS. And I'm going to do that using, sorry, I'm just going to draw another point here, point Z. That's where NS meets the circle. All right, so first I'm going to start out with an angle chase here that shows that arc, so you'll see later what I'm doing. I'll explain it more fully. But angle ANZ, that has to be 90 degrees since angle ANI is 90 degrees. Okay, so angle ANZ is equal to angle AVZ. Those are both 90 degrees. And so if angle AVZ is 90 degrees, then VZ has to be parallel to BC, since AV is also perpendicular to BC. And if VZ is parallel to BC, then arc VM has to equal arc MZ. That's because M is the midpoint of arc BC. So that would have to be true by symmetry, that arc VM is arc MZ. And so that means angle VNM is equal to angle ZNM. All right. So I'm going to do a little angle chase here. But basically, we wanted to show that angle TND is equal to angle SND, kind of like I mentioned before. But angle SND intercepts arc ZM, so we want to show angle TND intercepts arc VM. That's the same as showing that N, T, and V are collinear. So that's going to be my goal, and that's what I'm going to try to do here. All right, so angle VND, it's equal to angle VNM, which is equal to angle MNZ, right? Because arc VM is equal to arc MZ. And angle MNZ is equal to angle DNG, which is equal to angle DUG, which is equal to angle HUD. So I've written a lot here, but let's see what we just did. So angle VND is equal to angle HUD. Okay. But not only that, we know the reflection of the orthocenter H over the side of a triangle lies on the circumcircle. So HJ is actually equal to JV. And from there, you can actually conclude that NT and V are collinear. So I'm going to write this out just to make it more clear. Okay, so HJ is equal to JV because the reflection of the orthocenter over the side of a triangle lies on the circumcircle. And then GT and U we know are collinear, but if GUD, or in other words, if HUD is equal to angle VND and HJ is equal to JV, then it's not hard to see that U is basically the reflection of N over RD. So basically U and N are symmetric with respect to RD due to the fact that these angles are equal and the fact that HJ is equal to JV. So I didn't write that out 100% rigorously, but I'll let you look into it. It's not too difficult of a proof. And so by symmetry, if since HT and U are collinear, then NT and V have to be collinear. All right, so I'm going to draw in that segment. And once we know that, we can finish off the problem as I mentioned before. Because if NT and V are collinear, then since angle TND is equal to angle SND, because they both intercept the equal arcs of VM and MZ, and then also we know that angle RND is 90 degrees because RD is the diameter of this circle. Then it follows that T's, S, D, and R are in harmonic conjugation. Okay. And if we know that they're in harmonic conjugation, then we also know that GD bisects angle TGS. So like I mentioned, some of you might recognize this if you know about Apollonius circles. Really for any point on this circle, if we called it W, let's say, then WD would bisect angle TWS. Okay, so we have angle TGD is equal to angle SGD. And then we can finish off the problem just by subtracting this equality from this equality up here, BGD is equal to CGD. So I'm going to write that out. So we have angle BGH is equal to angle BGD minus angle TGD, which is equal to angle CGD minus angle SGD from these two equalities right here and up here. And that's equal to angle CGI. So angle BGH equals CGI, which solves the problem. So I'm sure there must be a simpler proof to this problem. I really like that I used the Sharkydevil configuration, which seems to come in handy quite a bit. But if any of you have a shorter way of proving this, I'd love to see it because I know there has to be one. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.